Okay, guys. So today I'll be doing this chapter on probability. It will just be a very quick one, okay, because of the limited time and the limited resource. Okay, I've decided to go through this probability first, before we head on to discrete random variable, because I believe this chapter is very important. Okay, so actually this chapter on probability, we all know, we have learned it before in secondary school. Okay, but there's actually a few concepts and some clarification that has to be made. Okay, and no doubt this chapter itself is one of the more difficult chapters when you talk about the JC syllabus. More difficult in the sense that it's very difficult to score. Okay, because a lot of people have problems counting the number of cases. Okay, which came from uh, permutation and computation itself. So the moment you miss a certain case, or the moment you shortchange yourself, or you count short of something, then the whole probability is wrong. Okay, and sometimes it's also very difficult for the assessor to actually give you marks because of the way the results are being presented. Okay, but nevertheless, we still hope that we can try our best for probability itself. Okay, and the one of the best advice that I can have for this chapter is when we do this chapter itself in the exam, we always assume that we are correct. Okay, can we don't spend too much time thinking about it, uh, pondering upon it. Okay, because at the end of the day, okay, you can actually get the marks from somewhere else instead of this particular chapter. Okay, so for probability itself, okay, this is actually confidence studies. Okay, we want to know what is the chances of something happening. Okay, so with that being said, actually it brings us to the very first formula over here. Okay, which is the theoretical probability formula. Okay, which tells us that it is actually the required number of ways, okay, over the total number of ways. Okay, this formula I think most of us know. So for example, what's the probability of getting a head in a conflict? Okay, so head in a conflict, so there's only one way to do it, and there's actually two possibility, which is head and tail. Therefore, the probability of getting a head in a coin toss is actually half. Same thing if there's a dice draw, what's the probability of getting a number six? So there's only one number six face on the die, okay, but there's actually six total outcomes that a die can produce. So the probability of getting a six is actually 1/6. So this formula is the most basic formula, and if you ask me, this is the formula that I really like to use. Okay, later on as you proceed, you realize that there might be different ways to do it. Some of your schools might be teaching certain different methods without actually going in depth into it. Okay, and you realize that some of the marking scheme, uh, they will be using different methods for that particular same question. Okay, that is when the doubts come about. What happened? Why is there this factorial here? Why they divide by this? And why did they actually include this number of cases? Okay, so these are some of the ambiguity that will happen along the way. Okay, so actually, what I want to do mainly here today is actually to address the some of the confusing concepts of probability. Okay, using a few examples. Okay, so number A, one simple event. So what do you mean by one simple event? Simple event is what I've already mentioned, getting a head in a coin toss. Okay, or in this case, find the probability of drawing 7 from a pack of 52 cards. So what's the probability of getting a 7 from a pack of 52 cards? Okay, so how many sevens are there in a pack of 52 cards? Actually, there are 4 sevens. So to get, if you apply the formula here, it will be 4 choose 1 over 52 choose 1. Okay, so the answer over here will be 4 over 52. Okay, very simple to apply. Okay, next, B. What is the if let's say we have two independent events? So what do you mean by two independent events? Two independent events means that the two events itself is independent of one another. One occurrence does not affect the other. Okay, in this case, this example very clearly showed getting a head from a coin flip and also a two from a dice throw. Clearly, whether or not you are flipping a coin or throwing a dice, theoretically is independent. Okay, and so getting a hit from a coin flip is actually, the probability is actually half. Okay, and getting a 2 from a dice throw is actually 1/6. Okay, so if you do it, it will be 1 over 12. Okay, so again, very, very simple way of doing. Okay, can. Next, for C, how about two conditional events? So the conditional events is actually the opposite, okay, the opposite of your independent events. Conditional events mean two events can affect one another. Okay, one of the easiest example to see is actually a secondary school example, whereby we want to draw from the same pack of cards. Okay, so what's the probability of getting an ace from two consecutive draw without replacement? Okay, so this word later on without replacement, I want to talk more about it. Okay, because this word itself will lead a lot of people down the wrong path. Okay, so in this case, let's do it in the secondary school way. How will we do it? So if let's say I want to get the ace for the first time, okay, it will be 4 over 52, correct? Because initially there's 4 ace out of 52 cards. So after I take the first ace out, okay, so naturally I know that there's only 3 more ace in the deck. So it'll be 3 over 51. Okay, so you'll be 452 times 3 over 51. And so there's the probability of getting an ace from two consecutive draw. So in this case, you realize that the second probability here is affected by the first probability because the first time round I've already taken an ace, so 4 becomes 3, and the deck of 52 cards actually becomes 51. Okay, so this is a two conditional events. And lastly, what we have here is actually the mutually exclusive event. So mutually exclusive event basically are events that cannot happen together. Okay, so example over here, getting a 1 and 7 from a single dice draw. Okay, so by throwing the dice only one time, you cannot get a 1 and 7 at the same time unless you are some god or gambler. The die actually break and show 1 and 7. Okay, so again, it's not possible. Therefore, the probability in this case is 0. Okay, so something not to be confused. Okay, like I always like to mention in class, the idea of uh, conditional events. The idea of independent events and mutually exclusive events. These two are different things. Okay, independent means they can still happen together. Okay, independent means they can still happen together. All right, but the probability is independent one. Mutually exclusive means that they totally cannot happen together. Okay, so a lot of students, because from the secondary school days, we actually like to see the event diagram. So if I have two events A and B, okay, if I draw these two A and B, so both diagrams show different things. The first diagram over here will show that okay, these two events can happen together because there's a form of intersection. Correct. The second diagram over here shows clearly a mutually exclusive event. So mutually exclusive means that A and B cannot happen together, so there's no intersection. All right. So the Venn diagram can only tell us whether is it mutually exclusive or not. Then the question comes, can a Venn diagram tell me whether is it independent? Independent. Whatever lah. Okay. So no, answer is no. The Venn diagram cannot tell me whether it's independent. Independent has to be tracked separately. It cannot be it cannot be seen from the Venn diagram. Okay, this is one of the major mistakes that a lot of people like to make. Okay, the Venn diagram does not tell us whether something is independent. It only tells us something whether is it mutually exclusive or not. Okay, so with that being said, okay, so we can say that from the example, we can see that, okay, so from example B, okay, clearly it says that if there's two independent events, A intersect B, okay, it can be written as A times B. Okay, the probability of A directly times to the probability of B. Whereas for case number C, example number C just now, here, okay, there are two conditional events. So two conditional events, we cannot multiply the independent probabilities directly. So how do we then compute A intercept B for this case? Okay, how can we compute A intercept B for this case? So now, okay, I'm going to use two methods. Okay, the first method is I will use my fundamental formula and count. So the fundamental formula we are talking about is actually this one. Required number of ways over the total number of ways. Okay, so let's count. So in this case, a lot of students will also ask. This is actually the essence. Do we count with order or do we don't count with order? So now I'm going to once and for all show it to you. Whether do you need order or you don't need order. So let's assume that there is order. Okay, let's assume that there's order. That means, okay, I will go ahead and pick the first card first. Okay, so if I pick the first card, it will be Ace. There's actually 4 A's. So 4 choose 1. Then I proceed with the second card, which is 3 choose 1. Okay, over 52 choose 1 times 51 choose 1. Okay, so this is with order. Okay, again, if you are familiar with PNC, with order, you can also write it this way. How can we write it? It can be written as 4 choose 2 times 2 factorial over 52 choose 2 times 2 factorial. Okay, so to represent order in PNC itself is also another very interesting point or interesting idea. You can represent the order by simply multiplication, or you can represent order by using factorial. Okay, but that is not the discussion for today. So this is with order. Okay, so let's say if I don't want to do with order, if I don't want to do with order, I don't care. Just 4 A's, I choose 2 over 52, choose 2. Okay, can? So in this case, with order, without order. Don't believe, take out a calculator and press yourself. Both answer will be the same. Okay, both answer is the same. So then the question is, do you need order or don't need order? A lot of people ask, whether it's order or no order. So don't need to care. Whatever that you think is correct, just do. But most importantly is you need to be consistent. If the numerator has no order, the denominator must also have no order. If the numerator have order, the denominator must also have order. Okay. Can so hopefully that answers the very important question of order or no order. Method 2. Method 2, we will use our conditional probability. So actually, the conditional probability was what we have done just now. What did we do? We use 4 over 52 times 3 over 51. This method is actually the conditional probability method. We have already unknowingly learned it in secondary school days. This is one of the favorite way to present our answer. 4 over 52 times 3 over 51. And same thing, you will produce the same answer, no matter whether you are using method 1 and method 2. In fact, if you take a look closely between these two, if you split up the fraction, they're actually the same thing. Okay, can? So hopefully you can understand what I'm trying to say here. It doesn't matter which method you use. It doesn't matter whether is it with order or without order. The exam papers, the solution I'm going to present to you every single time a different thing. Sometimes they can show you, sometimes, okay, they can show you this. Sometimes they can show you this. Sometimes they can show you the answer with factorial. Sometimes nothing. Sometimes they show you this. But if you have attended my lesson here today, you will know that they are actually the same thing. Okay? Can? So my personal favorite, okay, is of course this one. Don't need to say what. This is the simplest. I always use the fundamental formula without order, and I get my answer. Okay, I don't need to think too much. I don't need to worry too much. Okay, that will always be my fixed method to use. Okay, Ken. Hopefully you get my point. Okay, let's move on. So just now, actually between B and C, all right, between B and C, uh, there was actually, I paused for a moment, okay, because actually even for a die throw and a coin toss, if these two events were to be performed by the same person, biasness can happen. If I tell you today, if you throw a head and a 6, I give you $1 million. Do you think you will show biasness in doing it? Of course you will. So come on lah. Everything that you think of is actually conditional. Okay. Most of the events that happen is actually conditional. Truly very little events are independent. Okay, so let's look a bit further into this conditional probability. So as of now, before we learn into this formula, the conditional probability formula to us was just now, right? 4 over 52 times 3 over 51. This was the conditional concept. The first time I draw ace is 4 over 52. The second time I draw ace, because I've already picked one card from the deck, it will become 3 over 51. Okay, so the actual formula that we're going to use is A given B. Okay, which is pay A intercept B divided by PB. Okay, so let's try to summarize the whole thing by using this one simple example. Okay, so if I have a pack of 52 cards, okay, let A be the event of getting a heart. So let me label it. A will be the event of getting a heart. B to be the event of getting a king, jack, or queen. Okay, so let's say we don't know about this formula yet. We don't know about this formula yet. Okay, we use back our secondary school style to do it. So part 1. Okay, what is PA? PA, of course, you can write it as P heart lah. Okay, because the event is getting a heart. So PA is actually 13 choose 1 over 52 choose 1, because there are 13 hearts in the deck lah. Okay, 13 hearts, 13 spade, 13 clubs, and 13 diamond. So it's 13 over 50. Okay, simple. PB is what? Getting a king, jack, or queen. So there are 4 kings, 4 jack, 4 queen. So it's 12 over 52. So what is PA given B? Sorry, PA intercept B. That means I want to get a heart, king, heart, jack, or heart, queen. So if I were to use the fundamental formula, what is the fundamental formula? Number of required over number of total. So what is the required ways? Heart, king, heart, jack, heart, queen, right? In the whole deck, there's only 3. Total number of cards, 52. Okay, can. So today, PA intercept B is 3 over 52. Let's look at part 2. So what is PA given B? If you use the formula, A given B means what? I pick a heart given that it is a king, jack, or queen. Okay, can. So let's say I don't know. I don't know the formula. No. I write it down as the English. Heart, given that it is a king, jack, or queen. Then I use my fundamental formula, required over total. Sorry, total. Okay, can. So given that it is a probability of getting a heart, given it is a king, jack, or queen. So how many king, jack, or queen are there in the deck? 12, right? So the total is actually 12. But the required is only 3 pieces. Because I only want heart king, heart queen, and heart jack. So it's 1 out of 4. So same thing, I'm going to do it again. But this time around, I'm going to apply this formula. PA intercept B over PB. PA intercept B is calculated to be 3 over 52, which is from the first part here. PB is 12 over 52. It actually gives us the same answer. Okay. Of course, my take as a teacher is that please use this formula whenever possible, because we don't have so much time to go and count in the exam. If you can, please stick to this formula. But my basis of showing this is because to tell you that even for an example like this, it can be counted. You can always count by logic. Okay, you can always count by logic. Okay, so same thing, PB intercept A. PB given A, we can apply the formula A intercept B over PA this time. Okay, given A, so means over A. Okay, so the formula here, based on the formula, will be 3 over 52 divided by 13 over 52. So the answer is 3 over 13. Okay, can. So how about part 3? Part 3, you might think that it's a typo, but actually it's not. You might think, isn't it the same? Probability of A and B happening together. I want to find A intercept B. Okay, so you see, how do I get PA intercept B? Okay, so I'm not going to count or I'm not going to do anything. I'm going to use back the original formula of conditional probability. PA given B is equals to what? PA intercept B over PB. Meaning to say that if I cross multiply PA intercept B is equals to PA given B times PB. PA given B is a quarter times PB is 12 over 52. And the answer will give you back 3 over 52. So what does it actually show? What is this 1 over 4? 1 over 4 times 12 over 52. Okay, this is actually 1 over 4. 1 over 4 here is actually the conditional probability. So if I go back to here, just now the example, what I'm actually doing here is PB times PA given B. So to rewrite what we learned in secondary school, okay, to rewrite what we learned in secondary school, it's actually this. Can you see? when we use 452 times 351, the 351 is actually the conditional probability. The conditional probability of getting a second ace given that the first one is an ace. 351. Correct. Because we have already picked one card. Okay. I can tell you seriously here, this whatever that I've shown here is the essence of what I've learned on probability over these 20 years. Get it or don't get it? Okay, depends on your own enlightenment. Okay, some people don't get it, it's okay also, because we can just do the practice question, we can still go over it, no problem. But if you truly understand what I'm trying to say here or try to deliver here or share with you here, you will actually become very powerful for probability. Okay, can. Okay, good. So that's it for this part. Okay. So now we want to come to the solving techniques for probability. Here there's three solving techniques. The first one is the Venn diagram. Okay. Second one is the tree diagram. And the last one is your PNC counting. Okay. These are basically tools for you to solve a probability question. The core of the probability still remains the same. It's the required number of ways over the total number of ways. That one don't change. But you can use things like your Venn diagram, your tree diagram, or even your outcome table to help you visualize the number of cases. Let's look at 2.1. Okay. So for events A and B, is given that PA is 2 over 5, PA union B is 6 over 7, PA if intercept B prime is 1 over 3. Find the following. Okay, so let me just draw a simple diagram. Just change the color. Oops. Okay. A, B. Okay, and so what we are given is over here. So part 1, how do you find PB? Okay, so actually you can find PB by using this simple relationship. A union B minus PA intercept B prime. Where is A union B? A union B is actually the whole thing, correct? Where is A intercept B prime? A intercept B prime is this part. So does it make sense? If you use the blue minus the red, okay, you will get just P, B. Okay, so honestly speaking, if you ask me, how do I know I need to do that? Please memorize. Okay, other than that, either you memorize or you practice a lot of times, you know that this kind of question can happen this way, then you solve it this way. Okay, 11 over 21. Okay, part 2. Find PA prime given B. So this is a conditional probability. Okay, so we'll use the conditional probability formula. Okay, so no questions. It's always we straight away apply the conditional probability formula. Okay, so what is A prime intercept B? So if you draw back your diagram, A and B, A prime intercept B, which part is it? Okay, A prime means everything out of A prime, right? So A prime intercept B is actually this part. Okay. So again, we can actually apply a simple relationship based on what we have. We can use PB minus away PA intercept B. Okay, and over. Oh, so PB minus PA intercept B will give you this. Okay, PB means the whole of B minus away A intercept B, which is the intersection, which is this part. So minus away will give you the green color part. Okay, can. So the next problem is how do we get A intercept B? How can we get A intercept B? So to get A intercept B is the center part there, right? Okay, again, we can apply another formula. A intercept B, from what we have, we can write it as P A minus P A intercept B prime. Okay, can. So PA minus PA intercept B prime, from the first part, okay, you can see that PA is actually the whole thing, correct? PA is the whole thing, minus away A intercept B prime, which is the red color part. Okay, and then it will give you back the center, the same thing. So this center and this center is the same. Okay, so once you acknowledge all this, okay, we can just whack the numbers in. So this will be 11 over 21 minus away 2 over 5 minus 1 over 3, because all these are given values, over 11 over 21. Work it out, it'll give you 48 over 55. Okay, okay. So this is it for part 1 and part 2. Okay, the difficult part about this question is actually part 3 and part 4. Okay, so for part 3 and part 4, let's look at part 3. Let me look at this. Okay, part 3, a third event C is such that B and C are independent. Okay, so over here, it clearly tells you that it's independent. If it doesn't tell you it's independent, you cannot assume that it's independent. So PC is 2 over 5. So part 3, find PB prime intercept C. Since they are independent, okay, it doesn't matter is it PB or PB prime. So long as they are independent, okay, I can write it this way. Okay, PB prime will be 1 minus 11 over 21 times PC, which is 2 over 5. Okay, so the answer will be 4 over 21. Okay, so part 4. Part 4 is the difficult part. You need you to listen carefully. Find the greatest and the least value of A intercept B prime intercept C. So nowadays, a lot of schools like to make it very difficult by doing this 3. Okay, okay. So how do we know what is the least value of A intercept B prime intercept C? If you look carefully, where is A intercept B intercept C prime? It's actually this part here. So how big or how small can it be? How do we know? Okay, so you actually can see that, okay, what we have here, okay, from part 3 is PB prime intercept C. Where is PB prime intercept C? Based on this diagram, PB prime intercept C is actually this co-crescent. Okay, this whole crescent. So can I say that if today, if today, okay, I can shift the full crescent inside. This is A, yeah? This is B, yeah? If you can shift the full crescent inside here, this will be the biggest. Okay, and because initially it's this small part only, right? This small part. Okay, and so the crescent here indicates B prime intercept C. Okay, so if I can shift the full crescent into A, this will provide the biggest overlap for A intercept B prime intercept C. Same thing, vice versa, if, because A and B are fixed, if somehow I can shift the crescent out of A, then the intersection between A and this crescent is actually the smallest, which in this case this is 0 lah, because there's no intersection between A and B prime intercept C. So we are considering, if you look at this, we are considering the intersection between B prime intercept C and A. But this is the biggest and this is the smallest. So how do we know this is the biggest? Can this happen or not? That's my question. The answer is yes. But how do we know? We compare PA. PA itself is 1/3. Okay. Can. Sorry, is it PA 1/3? Oh no. We are not supposed to look at PA. Yeah. We are supposed to look at PA intercept B prime. PA intercept B prime is 1/3. Oops. Okay. Okay. To clear this. No. Let me try to shift.